Okay, so since you have to take the diagnostic test on Tuesday, I'm going to go over the warm-up questions for Lab 7 problems 1 and 3, and then just have you do Lab 7 problem 4 in lab. So the setup for Lab 7 problem 1 is basically you have a mass that hangs on the end of the spring. You raise the mass up a little bit and you let it go up and down, and it's in an oscillating manner. So first things first, I just drew a spring hanging from something that supports it with no mass. And so at this point, it's just going to be at its relaxed position. But when you hang a mass, it's going to go down a little bit, and it's going to go down a distance delta y if we call this the positive y direction. And because it displaces a little bit, there's going to be some spring force on there. So the second part asks you to draw a force diagram of the object when it's at rest or in equilibrium. So at this point, the weight is going to be a force downward, and it's going to be the mass times the acceleration due to the gravity in the y hat direction. And then there's going to be a force upward that's negative k delta y in the y hat direction. So I'm calling again the downward direction y. So if it displaces a little bit in the positive y direction, which is what I have here, the force is going to be upward because the spring force always goes in the opposite direction as the displacement. Then we can use Newton's second law. The sum of the forces in the y direction equals the mass of the object times the acceleration in the y direction. Since it's at rest, this is going to be 0 because the acceleration is 0. And so we can take the sum of these, and then we can use that to solve for k. So you've already done something similar like this when you just hung mass on a spring, and without letting it move up and down, you just measured the spring constant. And then part 3, question 3, so I just solved for y now, and then we're going to be asked to plot the displacement versus the weight, and 1 over k is going to be the slope. So as the weight increases, so does the displacement, which means that the slope of the graph is 1 over k, as that was the proportionality constant between y equals w over k. So then there's another part where you can find the spring constant by using differential equations and such to find the frequency, and then notice that the spring constant is going to be in there. So I'll go over and explain all that. But when the mass is lowered below the equilibrium position, the spring is stretched more than it was at the equilibrium position. So that means that the upward force of the spring is actually greater than the downward force caused by gravity. This is called a restoring force because the extra force upward by the spring is going to want to cause the mass to move toward the equilibrium position. So a restoring force makes the system want to get back to equilibrium pretty much. So again, I drew the same two pictures on the left with no mass, with a mass, but the system's at equilibrium, and then with a mass, but it's below equilibrium. So when it's below equilibrium, the displacement in the y from the equilibrium position, from this position, when there's no mass, is more than the displacement that it would be at equilibrium. So this means that the spring force right here is going to be more than mg. So the net force is going to go upward, and so is the net acceleration. And then in problem 2, I'm basically just defining YEQ to be the point on the y-axis when it's in the equilibrium position. So again, this relationship is going to be true because there's only two forces, and when you add them together, they equal 0. So these two have to be equal. So the main takeaway from here is that when it's stretched lower than the equilibrium position, then the net force is upward and the net acceleration is upward. Now, if it were to be above that, then the net force and the net acceleration would be downward if the mass was above the equilibrium position. So then the restoring force would be in such a direction that it would want to go back to the equilibrium position. So this is just kind of going over what I was saying. When it's above the equilibrium position, the net force and the net acceleration are going to be downward. Now, the spring force could still be upward if it's still not past the relaxed length. So the delta y, if it's between 0 and delta y EQ, it's still technically stretched a little bit, so the spring force is still up, but the gravitational force is more than that spring force, so the net force and the net acceleration is still downward. So, and the thing to note here is that it could still be going upward, basically from the momentum that's been carried from it going all the way down and then going back up. But the acceleration is downward because even if it's actively going upward, it's going upward slower at this point. And you may be able to see what I mean later. So with all this in mind, we can write a general formula for the sum of forces in the y being equal to the mass times the acceleration in the y. So what's going on here is this whole displacement is going to be the y of the equilibrium position plus the change from the y in the equilibrium position. So if this is the y in the equilibrium position, and at this point the sum of the forces is 0, then if there's a change from the y of the equilibrium position, there's going to be a different spring force, which means that the sum of the forces in the whole system is not going to be 0, which is why we have to include this extra term for our spring force. So one thing to note, when we solved the equation when it was in equilibrium, in other words, when the sum of the forces was 0, remember that mg minus kyeq equals 0. They're equal to each other, which we showed here. So moving back down, we can take these and subtract them together, and then that equals 0. So that just leaves the mass times the acceleration in the y direction is equal to k times the change in y from the equilibrium position. So we basically reduced it to something where the acceleration is in a equation with the change in y. So for part 5, I'm replacing where the origin of the y-axis is by saying that at the equilibrium position y equals 0. So that means that delta y EQ is just going to change to y, because y represents the change of where the mass is in the y direction from the equilibrium position. So placing all those things together, the mass times the acceleration in the y direction equals minus the spring constant times this new y that we found by setting y equilibrium to 0. So this is called a second order homogeneous linear differential equation. But this ain't Calc 3, so I won't tell you what that means, I'll just solve it for you. So you may be asking, well, how do we solve it? We use a very sophisticated technique called guessing. Yes, that's how you solve it, you guess something. So we have something where m d squared y of t dt equals negative k y of t. And then let's say that at t equals 0, it's at the equilibrium position, which means that y equals 0. So one equation that does work for that might be a good idea to try in our guessing. So the equation that we're going to try is y of t equals a sine omega t, where a is the amplitude and omega is the frequency of oscillation. So technically, because it's a second order differential equation, there should be 2 of these unknown coefficients. So it should be sine of omega t plus phi initial, but I forgot to write that. It doesn't make that a big of a difference because the phase angle doesn't depend on t. So when we take the derivative, that's not going to mess things up. But you should know that if you want to be more general, you should include the phase plus phi or something, plus phi initial. And then the amplitude that's another coefficient that resembles the initial conditions that we should include. So we have this equation, d squared y of t dt equals k over m times y of t. So we're going to say that y of t is a sine omega t. So let's take the derivative of a sine omega t, and that is a omega cosine omega t. So we take the derivative of sine omega t, and then which is cosine omega t, and then we need to use the chain rule inside the sine, which means we have to bring out the omega. So we need to find the second derivative of this in order to properly use it in our equation. So let's take the derivative of this, which after we take the derivative of this, it's actually the second derivative of this. So we do the same process and we get negative a omega squared sine omega t. So after we do all that, we note that if we use y of t equals a sine omega t as a solution, then d squared y of t dt is negative a omega squared sine omega t. And then also from the equation that we got from just using Newton's second law, we know that this also equals negative k over m times y of t. And negative k over m times y of t is a sine omega t, which means that negative a squared omega squared, sorry, not a squared, negative a times omega squared times sine omega t equals negative k over m a sine omega t. So we can factor out the negative a sine omega t and then note that omega squared equals k over m. So there you go. We found out that the angular frequency is the square root of k over m. So one other thing that you might notice is that this is actually generally called the simple harmonic oscillator. And if you break down Newton's second law for the simple harmonic oscillator, what you'll find is that if you get an equation for the acceleration, it's just omega squared times x. So if we took out this omega squared, negative a times sine omega t is just x. So this is kind of one of the techniques that you use a lot in physics if you're going to keep going in physics. To find the frequency of a simple harmonic oscillator. And so the last thing, this problem asks you to find the period of oscillation. So omega, or basically the angular frequency, equals 2 pi times the frequency. And the frequency is the inverse of the period. So you can do all that to find that the period of this simple harmonic oscillator is 2 pi times m over k.